with you all the details, including the registration link, which will be mailed to all of you. So those who are interested can please register and make use of this. So now, coming back to today's webinar, this Welding Tech Talk is being sponsored by Electronic Devices. So now I request someone from the Sigma team or the Electronic Devices team to introduce their company.
Vikram.
Vikram, I think
Thank
Vikram
you.
is there from.
Yeah, Vikram. Vikram, please start.
Vikram, yeah, you can
Yeah,
start.
thank you, Srinivasan sir. Good evening, everyone. I am Vikram on the behalf of Electronic Devices Private Limited. It's my pleasure to welcome you all. Today, I am here to showcase how our company seamlessly integrates in our day-to-day life. That making an impact in a ways you might not even realize that. To begin with, let me present a video that offers a glimpse into who we are, what we do, and the value we bring to your everyday experiences. Thank you. I'm showing you one video.
नो विक्रम, आवाज नहीं लगा फिल्म का?
Yes, sir.
फिल्म का आवाज नहीं है?
Hi, sir.
आवाज नहीं है फिल्म का?
Wait. So it's not audible.
Yeah.
No.
Wait, sir. Sorry. Now it's audible.
Okay. Yes, okay.
Okay.
By Sigma Weld. The toothpaste you rely on, sealed tight by Sigma Cap Seal, even the mouthwash that keeps you fresh, protected by our expertise. Every step of your routine, made seamless with us by your side. Even your safe and wardrobe, built to protect and secure, come from our welding expertise. The Nutella on your breakfast table, sealed with care by Sigma Cap Seal. From fresh juice to your children's favorite drinks, sealed by Sigma Cap Seal. As you commute, every vehicle you pass, cars, buses, trucks, and trains, runs with parts welded and heat treated by Sigma Weld and Sigma Therm. Even the lubricants that keep these machines running smoothly, sealed securely by Sigma Cap Seal. Your comfort at work is made possible through air conditioning compressors, shrink fitted with Sigma Therm induction heating and welded by Sigma Weld. From switch gears, pre-molded by preheating, to the everyday devices you use, like your old phone, all preheated for molding using Sigma Therm's dielectric preheaters. In healthcare, we continue to make an impact. Our heating technology enables precision in the manufacture of tablets and capsules. Each bottle is sealed, and every cap is assembled with care by Sigma Cap Seal. From the steel utensils that serve your family to the bottles of ghee and masala that nourish them, every product is sealed securely by Sigma Cap Seal. Every jar, every flavor sealed to preserve freshness, ensuring your family enjoys the best every day. From the plates on your table to the pickles you savor, our technology touches your life in every way. Forged, annealed, hardened, brazed, sealed, packed, joined, welded. At every step, from the smallest details to the biggest innovations, we are there, touching your life at every turn. Add ED to your thought, and we'll make it happen. As you begin your day,
Yes, sir.
Vikram.
Yeah, this was a small video that I have to present. Any feedback for the same?
So Vikram, you are done?
Yeah,
Yeah.
Okay. Thank you. Thank you, Vikram.
yeah.
Any
Thank you,
more
sir.
presentation, Vikram?
No, sir.
Okay, I will
So,
come back.
yeah. So Vikram, thank you so much for and thanks to you and Electronic Devices for sponsoring this Welding Tech Talk for so long. Yeah, we really appreciate. And coming back to the webinar again. So let me introduce Mr. Jurg, who is a Market Development Manager, Southeast Asia for the Nickel Institute. He is currently based out of Singapore. And Mr. Jurg is responsible for market development activities in Asian market, outside Japan and China, executing projects, developing opportunities and managing partner relations in that region. And prior to joining the Nickel Institute in 2018, he worked for Thyssen and then for Benteler, where he undertook for almost 25 years a number of special assignments. So Jurg is a Swiss national and who studied marketing, economics, and commerce in Switzerland. So thanks, Mr. Jurg. Now it's over to you to introduce our speaker for today's webinar.
Thank you very much, Dr. Krishnan, and welcome to everybody on the call. I would like to quickly introduce as well the Nickel Institute and as well IMOA. These are the companies that fund these events so that everybody can actually profit out of it. So I hope you all see what I see as well. So the Nickel Institute, it's what we do is we promote this and support the appropriate use in the appropriate applications of nickel and nickel alloys. We are a non-profit organization and we represent the majority, the leading mining companies that actually get nickel out of the ground and into our system. Still, even with the hype of batteries, where a lot of nickel is used, so still 70 to 75% of the nickel goes into stainless steel. That's why we focus that much on stainless steel and the education on stainless steel. And where we are located, headquarters is in Toronto, as well there where Gary sits. Then we have science and research labs in the US in Durham. We have a European headquarters in Brussels, very close to the EU board. Then we go over to Asia, where we have a representative office, a non-profit organization office in China, and one in Japan. Then we have rep offices in Australia, and I'm sitting in Singapore. IMOA is actually the same. They are representing the molybdenum industry. They are as well a non-profit organization. And as we all know, molybdenum is a key alloying element to improve the corrosion resistance and as well additional toughness and strength. So they are as well in every daily life. Molybdenum is used especially in the higher alloying when it comes to the transition of green energy in the industrial and building application and so on. But more important is actually the speaker of today, and that is Gary Coates. He is the technical manager for the Nickel Institute in Toronto. Gary is a metallurgical engineer who has worked in the stainless steel and nickel alloy industry for over 48 years, the last 25 with the Nickel Institute. He has worked in many different end-use industry and with fabricators to ensure the quality of the fabrication, to ensure long life of the equipment. He is actively involved with many professional societies in the corrosion, welding, and metals and mining industry. He has made so many presentations on all aspects of the use of stainless steel and nickel alloys. Gary is a professional engineer registered in Ontario, Canada, where he is based and is living as well. So, and with that, I'm very proud to hand over to Gary to actually start his presentation. And I wish everybody a very interesting and hopeful, with many questions, webinar. Over to you, Gary.
Okay, thank you, Jörg. And
Just
I will stop sharing.
thank you, Jörg, and thank you to all those at on the IIW. You do a great job, and we love working together with you. Let's see now. Let me share my screen here.
yeah, please share your screen.
There we go. Okay. So today we will talk about, we'll start a series on welding of stainless steel, some very practical aspects related to it. And today we'll talk a little bit about the austenitic and the ferritic and the martensitic series. Me here. So this is part one of a 6-part series. We will be talking on the next one about duplex and super duplex, followed by welding of nickel alloys, followed by welding of non-ferrous, and there we mean the nickel copper, copper nickel alloys, and we're going to include weld overlay there. Also, the ferrous and non-ferrous weld cladding will be an important one. That will be the 5th webinar. And finally, the 6th one is on weld corrosion causes and prevention. So I will be doing parts 1, 3, and 5, and Dr. Graham Sussex will be doing parts 2, 4, and 6. So you won't have to listen to me all the time. So today's agenda, I'll make some general comments about welding of stainless steel, including some misunderstandings that are commonly, or at least I've seen throughout my career. We'll talk about welding of austenitic alloys, and it will not be a really complete one on austenitic. We could talk all morning or all afternoon or evening, I guess your time, about them, and then some details about welding ferritic and martensitic alloys, and we'll allow some time for questions. So a few general comments, and I've done these some of these webinars before, and I always like to emphasize that the welder is a very important part of this system. Most of us are weld engineers or weld inspectors or non-destructive testing people, but the welding involves both science and manual skills. When I look at the American Welding Society journal, there's practical articles, and then there's articles that are deep into the theoretical metallurgical part of it. So it involves both, and melding the two together are so important. Welding involves a high level of skill. I really admire welders, their hand-eye coordination. And it's important for everyone, the welding engineer, to stay up to date. And it's important to train the welders in language and concepts they understand. So as a metallurgical engineer, I cannot use the words necessarily that I use to talk about welding with other welding engineers. I have to simplify it for the welders using concepts they understand. And we have to remember that most welders learn how to weld carbon steel. Once they become proficient at that, they usually move on to stainless steel, but they tend to want to use those same techniques they learned for carbon steel on the stainless steel. And sometimes that works, but sometimes it's wrong. And this is where the training comes in. It's really important to train them on the differences between the welding of carbon steel and stainless steels. So welding is critical to successful fabrication of stainless steel. And we really have to ask ourselves, especially as welding engineers, what is needed? Is this for corrosion resistance? So I have to weld it to optimize the corrosion resistance, or the high temperature properties, the properties of interest, in which case it's maybe a completely different set of rules for the stainless steels. In carbon steels, the key properties are strength and ductility, and sometimes when you get into structures, fatigue or toughness being the low temperature, lack of embrittlement. Stainless is used in these applications because and we do the strength and ductility of it, but we don't test the fatigue or toughness of them, and we don't test the corrosion resistance and high temperature properties of them for the welder. So one of the things that people, welders often say when they're showing off a weld is, this is a good looking weld. And that is important, but it's not necessarily a good weld if they've used the incorrect filler metal, or sometimes no filler metal where filler metal is actually needed, or they used an unsuitable welding procedure, too high heat input, for example. The weld may look good, but it may fail quickly in service. And of course, they do not see that. We all know that there are 5 main families of stainless steels: the austenitic series, the 300 and 200 series, ferritics, the duplex austenitic ferritic ones, martensitic, and precipitation hardenable. And of course, there are major differences in weldability, not only between the different families, but within the families, and especially between the low alloyed and high alloyed stainless steels. One has to remember there are hundreds of types, and in North America with ASTM, we use the word type preferably instead of grades or alloys when referring to the ASTM standards. But there are hundreds of types of stainless steel. And for example, ASTM A240, which is the plate, sheet, and strip specification, there are close to 200 different types or alloys listed. In some of the other ASTM standards for other product forms, there are even more alloys listed. So there's a whole group of alloys there that some were very familiar with, and some were not familiar with very much at all. And of course, in different national standards, there can be variations of many of these grades too, and grades that aren't included in the ASTM. So it is really critical for the welding engineer, the quality assurance guy, the foreman, to know the exact alloy being welded. Now, I'm posing the question, is it important for the welder to know that? And so I'm going to take a few cases here. First of all, the chain is only as strong as its weakest link. That's a common expression we use. And if the chain breaks, the chain is essentially useless. So if the welder is not, if the welding engineer has specified it right, but the welder is doing it wrong, essentially the weld is bad. And the welds in a stainless fabrication are usually the weakest link. So let's take a couple of misunderstandings that I have come across. And so the first one The welder knows that 308 filler metal is the matching filler metal for 304L, but after finishing most of the components, he ran out of 308L, decided to use 316L to finish the job. And after all, 316 is higher alloy. It's got molybdenum in it, a little higher nickel content, and it is more corrosion resistant than 308L. Was what he doing correct? Well, in most cases, 316L is more corrosion resistant than 308L, but there are several exceptions, one of them being nitric acid, where 308L, 304L is more corrosion resistant than 316L. And there are some high temperature applications where 316L will embrittle, where the 308L will not embrittle as quickly. So we need to explain to welders that they need to ask a qualified individual whether a change in filler metal is allowed. Now, if you were doing something very strict in the nuclear industry, you know, there would be probably no question about the welder changing the filler metal on his own. But in many plants, and especially when there's fewer people around, he may make the decision himself. So another example on a 316L tank, a welder, he did the qualification testing using 308L filler metal on 304L plate. That qualified him for welding the ASME P8 Group 1 material. His weld, he passed the bend test, and maybe a tensile test was done too. And then he was given the 316L shielded metal arc electrodes to weld up the tank, but they didn't weld as nicely as 308L he had used in testing. So he switched to 308L. And why not? They passed all of the tests that he had to do. And of course, most of us know that that is completely wrong. 316L in this particular case would have a higher corrosion resistance to the tank media. And very rarely do we ever do corrosion testing as part of the qualification. So the welder hasn't understood that, okay, even though both meet the ASME P8 Group 1 material qualification, there's a difference of why the different alloys are used. And therefore you did it wrong. Now, some of you might say, oh, that'll never happen in my shop or in my chemical plant. But in reality, I was involved in a case that actually didn't involve 308L and 316L. It involved duplex and super duplex, where they got qualified on 2205 material. The component was actually the super duplex alloy, and they welded it. The shop foreman and the welders were all happy to weld it with 2209 filler metal, the one for 2205. And of course, they even delivered the component to the end user. And then it was discovered that, wow, this is completely wrong. The whole job is essentially scrapped. You have to grind out the weld and re-weld it, and you get actually still an inferior product. So this actually does happen. Hopefully it's very, very rare, but the welder in this particular case, the welding foreman, didn't understand the difference between qualification welding and the welding in practice. And a third example here, and again, from my past experience, we were doing some training of welders and welding foremen at a chemical plant in Canada here. The chemical plant handled some very corrosive, nasty chemicals, hydrofluoric acid. If you've ever worked with that, you know that it is extremely dangerous for personnel. We had a question at the end of the a question period at the end, and one of the welders asked why we didn't talk about the electrodes that could be used for many different stainless alloys, and we didn't quite understand what he was talking about, and he explained that they used 310-16 for welding all stainless steels between 310 and 316. And again, I mean, we were all shocked, literally horrified to hear it. The other plant engineers were horrified too that this was actually happening. And again, training the welders into what the classification, the -16, I'm sure you all know that it's the type of coating that's on the coated electrode, but you know, the welder and he probably was told by somebody else that this was the case, and that's what he used, and that resulted in a very dangerous situation where a material that shouldn't be used for that particular job was used, and there's possibility of major leaks and danger to the personnel. Something similar is that, and I've seen it a few times, is that we've been told that an alloy such as 347 has very high corrosion resistance, and they know that, or they believe it is true because the number is higher than 316L, 317L. And you can sort of understand where that's coming from, that, you know, 316L is a higher number than 304L, usually more corrosion resistant. 317L is higher number than 316L, more corrosion resistance. But it's, of course, completely wrong. And we've seen this both in North America and in Europe. So let's move on to the talk about austenitic stainless steels. And over 75% of all stainless steel produced is an austenitic type. So if somebody says, I've welded the stainless steel before, chances are it was an austenitic grade, and most likely either 304 and its variants, the 304L, 301, 302, are really the most common steels entered. If you encountered, rather, if you understand that work in a chemical plant, you know, 316L is extremely common too. And so welding 304 is, of course, as we all know, initially challenging for a carbon steel welder. But when you go to welding some of the higher alloyed austenitic alloys, 904L, the 6-moly family, that's grades like 254 SMO and AL6XN, and some of the heat-resistant alloys, they're even more challenging, requiring slightly different welding parameters, and in some cases, some major changes over what they do. So just because somebody says I've welded stainless steel doesn't mean that they really know what stainless steel they should be welding. It's up to us to make sure they understand what are the important differences here. So there's lots of things I can talk about in austenitic stainless steel. I'm going to focus mostly on the ferrite content. Most of us know that many, not all, of the austenitic filler metals have a composition designed to result in a certain amount of ferrite in the weld metal. And the reason for this is to prevent or at least lower the risk of hot cracking in the weld metal. So there are a number of misconceptions about this, less among, of course, weld engineers, but among welders. They hear ferrite and they think ferrite is iron. And of course, the chemical symbol for iron is Fe. And so they think ferrite is iron. Of course, ferrite is not iron. It is a metallurgical phase. Ferrite, austenite, martensite, those are crystal structures there. So in itself, it's not necessarily dangerous, but since all stainless steel has iron, there's a perception that, okay, well, there's iron in stainless steel, so that is my ferrite content. That's how I get it. It's the amount of iron. Well, no, that's not it. And secondly, people add ferrite, or the manufacturers of electrodes and wire add ferrite to the wire or electrode, something you add. And no, it is the composition that determines it, and the composition of both the wire, and if there's a flux involved, the coating on the flux. And so the amount of ferrite that forms is determined by the composition of the wire and the coating, and also involves the cooling rate of the weld. So a faster cooling weld will have a different ferrite content than one that is slowly cooled. Not a huge difference, but something that's important. Now, most of us are familiar with diagrams that describe the ferrite content of a weld, and they're very useful. They'd only give approximately the ferrite content of the weld. You can't use it to say, okay, that we get 8.5% ferrite. That's what I calculated, and expect to actually get 8.5. It could be plus or minus maybe 2% in ferrite for the actual weld. The Scheffler diagram, which I've shown here, I like the Scheffler because it shows from between 0 ferrite, no ferrite, and 100% ferrite. It has a lot of advantages in certain areas, but it doesn't show nitrogen. So the vertical axis is, we call it the nickel equivalent, which is made up of both the nickel content, the carbon content, and the manganese content. Really, nitrogen needs to be in there, but it's really difficult to measure nitrogen that actually goes into the weld metal, because the arc, when you go from the wire to the base metal and transfer the droplets of molten stainless steel, they can pick up nitrogen. So you do make some assumptions about the nitrogen content there, and there are diagrams that include nitrogen. And of course, on the horizontal axis is the chromium equivalent, which is chromium, the molybdenum, silicon, and to a very minor extent, the niobium content. But it is important to have, when you're using these diagrams, the actual chemical composition of the filler metal. I was actually shocked when I was younger that we got mill test certificates for the welding filler metal from a number of manufacturers, and they weren't actuals, they were typicals. And the typical is pretty useless. The electrode you get might be close to the nominal value, but it may be different from that. So you need to ensure, if you're using these diagrams, that you have the actual chemical composition of the filler metal. And you must take into account the amount of dilution of the base metal, because these diagrams are made for 100% weld metal, but in welding, you do get dilution from the base metal, and the base metal will generally have a very low ferrite content theoretically when you plot it out on these diagrams. So I'm going through a series of questions here. Do 300 series rod alloys, plate, sheet, bar, pipe, etc., do they contain ferrite? And the answer is basically most of the rod alloys contain 0 or close to 0% ferrite in them. 304, 304L today especially may have up to 2% ferrite present. So it is the exception that people are keeping the chromium, the nickel content, and in molybdenum containing grades, the molybdenum content right down at the bottom end of the specification. And that has meant that, especially the 304 grades, they may have up to 2% ferrite present. Now, maybe you say, well, I've done a ferrite measurement on some 304, and that shows that there's much higher percentages of ferrite there. Why is that? Well, these gauges depend on the magnetic response of the material, and while ferrite is ferromagnetic. It responds to a magnet. So is martensite. And martensite is easily formed in 304 and similar alloys due to cold working. So that's things like forming or stretching or rolling it or machining it, even left over from a cold finishing operation at a stainless steel mill. So if you measure the base material, the plate, for example, with a Magna gauge or Fisher ferret scope, it may show a higher level of ferrite than is actually present because it is also detecting martensite. So most of you understand that CAS 300 series materials are higher in ferrite content than the plate sheet bar, etc. And that's because foundries, most often, they have very limited refining capabilities. They can't take out things like sulfur, which are when present in larger amounts, can result in the hot cracking of the material. So they intentionally have a higher ferrite content, and sometimes they will make it on a 304L type cast material up to 20% ferrite. Very high levels, higher than you would ever see in a weld electrode. And you might ask, is ferrite detrimental to the performance of a stainless steel, corrosion resistance, or high temperature properties? And the answer is, yeah, in many cases, it can be. So when the ferrite level is less than 10%, is generally not detrimental. But higher ferrite levels may decrease the corrosion resistance, not in every environment, but in some environments. And even a small amount of ferrite may be detrimental to corrosion resistance in a very few cases. And often in those cases, the engineering company involved with the welding will specify a maximum ferrite content in the weld of 2% or even lower. For urea grade materials, they often say 0.6% maximum ferrite in the welds. In high temperature applications, ferrite can embrittle with time. It can become brittle. If you have a small amount of ferrite in an alloy, you have a series of hard particles. That generally is not a problem. It actually makes the material a bit stronger. But where you have high ferrite welds, 10% or higher, you can lead to cracking in service. Now, all that takes time, so you don't see it right away. It might take a year or two before it actually fails. So there are some filler metals that have 0% ferrite. So which ones and what do I have to do about those? Well, the most common ones that have 0% ferrite are the filler metals for 904L and the 6% molybdenum alloys, which are used in corrosion applications, and the high temperature alloys such as 310 and 330. They have 0% ferrite in the filler metals, and you have to be very, very careful when welding those alloys, lower heat inputs than you would for standard grades. Cleanliness of the weld joint is very important, and even a highly constrained joint where as the weld cools and shrinks, and it puts stress into the base material. If it really can't move, then it can easily lead to hot cracking. And what stainless steel filler metals have high ferrite contents? Well, 309L, 309 and a variation of that called 309 MOL. They have higher ferrite contents than 308L, 316L, and they're especially used to weld carbon steel to stainless steel. Carbon steel contains can contain contaminants such as a higher sulfur content that can lead to hot cracking, but also you have a thermal expansion mismatch between the two, so you have a more highly stressed joint there. 312 has the highest ferrite content. It is used for more difficult to weld materials. It's sometimes sold as an electrode that welds anything, which is not true, but it is more useful and is often used as a maintenance electrode, not in chemical plants or pharmaceutical or even the food industry, but in maintenance repair shops that do a lot of occasionally a little bit of stainless steel welding. But basically 312 is a little more is forgiving. It's easier to weld with. The welders like it. But because it has a very high ferrite content, you have to be very careful where you use it. And why are some stainless steels welded with nickel alloy filler metal? Well, the high molybdenum alloys, 6-7% molybdenum stainless steels, the 254 SMO, Al6XN, etc., they cannot be welded by a matching filler metal, as the weld would have significantly lower corrosion resistance if it were done with a matching filler metal. So you have to use a very high molybdenum filler metals, the 9% molybdenum, which is the 625, or nickel chrome moly 3 electrode is most common for the 6% moly alloys, but the C family of alloys, Hastelloy C276, C22, and some of the other brand names there, they can also be welded, and they have even higher molybdenum content, anywhere between 11 and 16%. So they are more corrosion resistant than the base metal. And those alloys, of course, cannot be welded autogenously, that is, without filler metal. Now, another question is, can I weld one austenitic stainless steel with a higher alloyed austenitic filler metal? For example, can I weld 316L with 317L? Is there a problem there? And the answer is, normally there is not a problem. Yes, you can normally do that. You do have to ensure when we say higher alloyed filler that it is actually more corrosion resistant or more oxidation resistant if it's a high temperature application than the base metal for that particular application. In general, 317L is more corrosion resistant than 316L, so 99% of the cases that's valid, but you have to be aware of the exceptions. And the technique of using a slightly higher alloyed filler metal is fairly common when doing in the field repair welds. And in the field repair welds, you can't get the same level of maybe cleanliness, and the external environment isn't all that clean. It might be hot and humid, and so it helps to make the weld metal a little more corrosion resistant. There's a number of chemical companies, pharmaceutical companies that will do this. So what are the most common problems encountered when welding 300 series stainless steels? Well, the first ones, just taking from my experience, is distortion. The 300 series have a high thermal expansion coefficient compared to carbon steel, compared to the other types of other families of stainless steel. And so distortion is really the number one concern that we have actually, in my experience. And it's also very difficult to combat. There are things like, you need more tacks in when welding together plate, and you need to use a lower heat input. Then the high heat inputs will cause more distortion than the lower heat inputs. a number of factors come into it, but distortion is the number one issue I see that people face. Welding is similar metals, again, because of the difference in thermal expansion coefficient when you're trying to weld them together. It's not easy. There are complications when welding some of the copper nickel alloys to stainless. You have to use a butter pass or an intermediate pass. You can't weld the two directly together in some cases. Also, lack of fusion, no root gap because the austenitic filler metals have a lower penetration rate than what you are used to with carbon steel. And I can't help but to include trying to weld at high production rates. Everybody wants to weld more, so you turn up the amperage on your machine and try to do it faster, and that can lead to micro cracking and distortion and a lot of repair welds that go on there. So you actually weld faster, you fill the joint faster, but then you have a lot more work afterwards. I'm no expert on welding the 200 series stainless steels, and for those who are not familiar with them, these are austenitic alloys that are high in manganese and often have high nitrogen, and the idea is that then they have those two elements can replace most of the nickel in an alloy. They are used a lot in thin sections for maybe the food industry, a few other applications, but generally not in the chemical or petrochemical or pharmaceutical industry. They work hardened more quickly than the 300 series. Sometimes they will add copper to them because that lowers the work hardening rate. Work hardening of the material can occur as the weld solidifies and shrinks, so it's pulling the material away. These materials are often welded with the 300 series filler metals. And I just show an example of a large water tank. It was built using a 200 series stainless steel, maybe, I think it was about 15 millimeter thick plate on it. There were numerous micro cracks in the structure, which were not obvious to the welders. And when they filled the tank full of water, there were quite a number of cracks that looked like this that needed to be re-welded again. So there can be some issues with thicker 200 series, not so much on the thinner materials. In the time remaining, I want to move on to the ferritic and martensitic families. There are two families that have a great number of different alloys in them with varying properties. So we can only talk about broad guidelines here on weldability and welding. And we think of these two families as being very different. The ferritic stainless steels are not hardenable by heat treatment. That's one of the goals there, where the martensitic stainless steels are hardenable by a quench and temper mechanism. But what is complicated and not really well understood is that when they call a weldable ferritic alloys, and they're used especially in thicker sections, they're actually a duplex grade, although not the austenitic ferritic duplex, but a ferritic martensitic grade. You're familiar, I'm sure, with 3CR12. The Europeans call it 4003. In North America, we have a 409 nickel. They all have a slight nickel content, and they are not truly ferritic stainless steels. And I'll talk briefly about them later. And one of the most challenging issues I have when somebody phones up and he says, how do I weld 410 stainless steel? And you know, the first thought is, well, 410, that's a martensitic stainless steel, but is it? Is it 410 with the actual higher carbon version of 410, which can have as high as 0.15% carbon? Or is it 410S? That's a more weldable grade used in plant construction, which has an 0.8 carbon max. Or there exists a 410 low carbon version, which has 030 carbon max, just like a 304L or 316L. Now, if we had 0.15% carbon, the alloy would react to welding like a tool steel. In other words, it would rapidly harden in the heat affected zone during welding and likely to crack if there was no preheat. If it was the S grade and let's say had 0.06% carbon, the alloy would harden slightly in the heat affected zone, fairly easily welded, usually a low preheat, and if it's thin enough, maybe no preheat at all there. If you didn't have the preheat on thicker material, it could crack, but that's only on thicker material. And if the carbon content was 0.01%, the alloy wouldn't harden at all. It would actually be a truly ferritic alloy. So even though 410 is a martensitic alloy, the 410 low carbon is essentially a ferritic alloy. So you can see it is not, it is complicated. So I won't spend too much time on the properties of ferritic, but they're basically a single phase, the ferrite phase. There's often titanium or niobium there to tie up the carbon and nitrogen. Nitrogen can be very detrimental in ferritic stainless steels, so they want to keep the levels down low, and what level there could come from welding, you want either titanium or niobium to tie it up. A truly ferritic stainless steel doesn't harden with the heat of welding, although it may become less ductile and less tough. They have a comparatively high ductile to brittle transition temperature, which is alloy dependent. Sometimes it can be minus 30, minus 20. Other times it's around room temperature, and that ductile to brittle transition temperature can be even above ambient temperature. So you have to use them very carefully when you get into colder environments. The thermal expansion rate is less than austenitic stainless steel, more similar to carbon steel, a little bit higher than carbon steel, but much, much closer to that than the austenitics. The thermal conductivity, the heat transfer through the material, is much higher than an austenitic stainless steel, but still lower and significantly lower than a carbon steel. And they're susceptible to hydrogen embrittlement, and I mention that primarily because if you have moisture present, whether in on the base material or on the welding electrode, you can get hydrogen released, and you can get an embrittled weld. Grain growth in the heat affected zone is the most often is the issue on thicker material of these purely ferritic stainless steels, reducing ductility, and often thicker material is not available because the thicker material from the mill will have a large grain size. So it's very difficult to make some of the pure ferritic stainless steels in thicker material. Some of them are welded with a ferritic filler metal, some are welded with an austenitic one, and some can be welded with either. And there are advantages and disadvantages to using one or the other. This is just a list of grades, and I just picked some at random here, but I divided them into the three families. That's my own divisions. One is the 11% chromium alloys. 10.5% is the minimum to call it a stainless steel. So these alloys are right at the very bottom end of the chromium content, and therefore the corrosion resistance. And then the ones in orange, they are a little higher in chromium content, and I call them more standard ferritic grades. And then we get into the high alloyed and super ferritic alloys, and we'll talk about each of those families. But 444 or 18 chrome 2 moly is a grade used. In some parts of the world, and then there are some very specialized, normally proprietary grades that fall into this category. So in general, let's talk about the 11% chromium ones, various types of 409. They don't form sigma phase or a 475-degree embrittlement. And I'll explain the significance of that in the next slide. But they're the only ferritic stainless steel alloys that do not. So because of the low chromium content, they don't form sigma phase or the higher temperature embrittlement there. Generally, you find them in thinner sections, less than 6 millimeter or quarter inch, but they can suffer from grain enlargement in the weld and heat affected zone in heavier sections, which results in low ductility. They can be welded autogenously or with filler metal if needed. And there are some matching filler metals where you're using them especially for automotive exhaust systems, which is high volume. If they can't be welded autogenously, they'll use a 409 type filler metal, and either gas tungsten arc or gas metal arc welding is used, and 309 can be also used on these alloys. If we move on to the higher chromium ones, 430, 439, 446, they're not so common in the chemical, petrochemical industry, perhaps the 446 for some high temperature applications. They can embrittle by sigma phase in this 475-degree embrittlement. And why I mention that is that if you're trying to do a weld repair on ones that have been in service at that temperature, they may not be possible to weld repair. They may be so brittle that you cannot weld repair them. Again, the grain growth is a problem. You can weld them autogenously in thin sections or with a filler. There are theoretically available matching filler metals for 430 and 446. They can be welded with a 300 series filler metal too, if appropriate. The 446 is often used where you don't want nickel, and so therefore welding them with a 300 series is not a suitable way of welding them. You want to weld them with a matching or a ferritic filler metal. And most of these alloys, you don't need a preheat. You do want a low interpass temperature and low heat inputs on them. And that's all to prevent grain growth. And finally, the high alloyed superferritic alloys, generally only thin sections. Some of those superferritic alloys, the maximum thickness is produced at the mills. And I just see a mistake there. It should read only up to 2 millimeter, not 2 meter, 2 millimeter in thickness. Please correct that in your mind. I'll correct that when I give out the slides later. And it's used mostly as heat exchanger tubes, these alloys. Very careful welding procedures, very low heat input. Read your guidelines for the specific alloy. Cleanliness and a fully protective purging are critical. Occasionally, a matching gas tungsten arc filler metal is available. Otherwise, an austenitic one may be used of the appropriate corrosion resistance. These are all used in corrosion applications. I mentioned about the weldable ferritic stainless steels, which are actually ferritic martensitic grades. I know in India you're producing a number of them, and they do have their applications, and especially in structural applications where you can use the strength of them. And because they're lower alloyed, they're also lower cost. So they have resistance to inland atmospheric conditions, not near the sea where you have salt spray and chlorides present. So, as I say, the corrosion resistance is near the minimum for stainless steel. They are available in thicker sections. I've seen them up to 25 millimeter, perhaps thicker is available. They don't have the same issues with grain growth, of fast grain growth in welding, although it does happen. They do grow in grain size in the heat affected zone. Generally, it isn't the same issues as with the purely ferritic. Generally, they're welded with 309 filler metal. Most welding processes are suitable there for them. You have to think ahead what properties you want in the weld and heat affected zone to ensure that you meet the requirements in terms of its strength, the ductility, and toughness. You can get these materials in strength levels that are stronger than the 309 filler metal weld properties. So then you end up with a lower strength weld, higher strength material, and that generally is not acceptable. So maybe somebody in one of you metallurgists in India there will help to solve that issue, come up with a filler metal that actually is suitable for welding the higher strength versions of these alloys. I'm going to just briefly talk about martensitic alloys. You can divide them into three categories. A lot of these the lower carbon versions are used in the oil and gas industry. And so the ones that have less than 0.06 carbon, typically maximum hardness is 35 Rockwell C. There's an intermediate carbon level that gives higher hardness, 35 to 55. And then there are the grades that you really want hard, 55 to 65 Rockwell C, and typically they have more than 0.30% carbon, so very high carbon content. So just as a reminder, they're soft in the annealed condition, then you harden them by heating them up to a certain temperature and then quenching them, and then you temper them to bring back to lower the hardness to whatever hardness level you want. In the quenched condition, they can be very brittle. So, and one of the problems with the complications, shall I say, when welding martensitic stainless steels is you need to determine what properties you want in the heat affected zone and the weld metal. Can you live with a weld that is weaker but more ductile? Can you live with a slightly harder heat affected zone than the base material? And if you really want uniform properties, well, the one way to do it is to weld it in the annealed condition, re-anneal it, then go through a hardening and tempering treatment again. All that adds cost and difficulty to welding them. So these are particularly tricky alloys to weld. I show this graph. It's actually a martensitic stainless steel welded without filler metal. So you can see on the left-hand side where the fusion zone is, the distance from the fusion line. So the weld metal is a little bit harder. Then there's a bit of a weaker area right at the fusion line. Then you go back to the higher hardness, and then it starts dropping as you get to the base material. But there's even an area that's weaker or less hard than the base material right at the boundary between the heat affected zone and the base metal. So I'm only showing this because welding martensitic stainless steels can be complicated. Very briefly, similar welding characteristics to tool steel as a general statement. You want to do a preheat, minimum interpass temperature. You want to keep the interpass temperature high. Post-weld heat treatment is often needed. You have the choice of filler metal, soft and ductile, or hard and brittle, unless you do a heat treatment afterwards. The ones used in the oil and gas industry generally are the low carbon ones. You usually use preheat and heavier thicknesses, slight preheat maybe on thinner sections, mostly to make sure you remove any moisture from the surface because they are sensitive to hydrogen that may form when you weld a wet material or moist or material. The preheat temperature is often relatively low, 120 degrees C. Post-weld heat treatment may or may not be necessary. Obviously, you want to try to avoid it, but it may be necessary. Most of the time, they can get away without doing post-weld heat treatment. And certain alloys and certain uses, especially in hydrogen sulfide services, you might need to do a double tempering operation. So you temper it at one temperature and then temper it again at a slightly different temperature. The intermediate carbon levels, of course, as the carbon goes up, the hardness will also go up. And generally, you want to use preheat in thinner sections with an increased preheat temperature as you get thicker there. And you want the interpass temperature usually just below the MS value for the alloy. Those of you who are metallurgists know what that is, but I have to be reminded sometimes, but that's the temperature at which austenite begins to transform to martensite in a steel, and it varies with the alloying content. Generally, the intermediate carbon alloys, you do want to do a post-weld heat treatment, even if it is just a tempering operation to get the best properties. And finally, we come to the higher carbon martensitic stainless steels. Obviously, when you get to Rockwell C55 or to 65, they are very, very hard. They are very, very brittle. You do need to preheat for all thicknesses with an interpass temperature above that MS line. And they are tricky to weld. To avoid cracking in welding, very, very small welds, very small, low heat inputs there. But you also want them to cool to allow hydrogen diffusion because they are so sensitive to hydrogen that it's hard to avoid getting hydrogen into the weld. And generally, if you really want the best properties, you do a post-weld heat treatment. So in summary, for the ferritic and martensitic alloys, each case of welding ferritic or martensitic needs to be examined carefully. It isn't sort of, well, I can use my general rules and I'll be safe. No, you need to really look at what particular alloy you want and what actually properties you want of the heat affected zone, especially, and the weld metal. And even different compositions within the same grade can weld significantly different. Oops. And so there's a number of different publications on our website, the Nickel Institute one, and the AMOA website also. We do offer a free technical help service. So if you have any particular questions, you can go to the web address there and then you can enter your question, and we generally can reply within 2 working days. We have a series of of consultants around the world that can help, and especially when it comes, for example, oil and gas or with food industry. They will be specialists in their particular area, and we'll send it to the appropriate person. So that's all I have.
Yeah,
I
thanks,
think
Gary, for this wonderful session. And I think there are a lot of questions in the Q&A. If you can just go through at least few of them.
yeah, okay. Let's just see now. Just going through the chat. Oh,
We have to go through the Q&A.
Q&A. Oh.
Yeah. So that will be on the top of your screen.
Oh, there it is. Yeah, okay, got it. Got it. I got it. Okay, when welding 321 or 347 for high temperatures, recommended to carry out a local post-weld heat treatment on the welds. Okay, so if you weld 321, which is titanium stabilized, or 347, which is niobium stabilized, the idea is those elements, titanium and niobium, you want them to tie up the carbon content. But when you when you weld them, you don't tie up all the carbon content. And so when they're used at high temperature, if the carbon is not tied up as a niobium or titanium carbide, it will tie up with chromium, and that reduces the corrosion resistance. And this is very important when you have hydrogen sulfide in a line, that when cooling and down, the hydrogen sulfide will form polythionic acid. It's called. It's a chemical where hydrogen sulfide combines with water in an air environment, and it will crack these alloys. So typically, most oil and gas people, where they know that this is a problem, they will specify what we call a stabilization anneal, which causes all the carbon to be tied up with either the titanium or the niobium. There are different procedures. Different oil and gas companies have different, slightly different temperatures what they think is optimum for there. But so it is common to do that. And sometimes in my own experience, you have to remind the fabricator that this is required for that. They will often have a stabilization anneal on the plate material in the first place. Do they want it on the weld? And ideally, you do want it on the weld. The next question relates to superaustenitic stainless steels and brine service application. Yeah, so the 6% moly alloys are used there. The S31254 is it's the 254 SMO. Yes, that is used there. Typically welded with a nickel chrome moly 3, which is the 625 type nickel alloy there, and it performs well. I might just throw in that the super duplex alloys are also used in those kinds of applications also. There's a following question. What heat treatments are required to be done? Okay. Yeah. So the 31254 alloy, the 254 SMO alloy, the minimum heat treatment temperature for that alloy is, according to ASTM, 1150 degrees C. In practice, the mills actually go higher than that, 1180 degrees C. For castings, which are thicker, they'll even do 1200 degrees Celsius. Very, very high temperatures. It's a problem because the material becomes very weak at that temperature, so it actually will just deform on its own weight. So you have to make sure they're supported well. If it's a dished head or something like that, you have to really support them, and so they don't collapse on their own weight. And you do have to quench it quickly afterwards. And that's also because in quenching you can have deformation. So usually if it's thinner material, you can use a forced air. You want it to cool fairly quickly, so you used a forced air or maybe a light water spray. If it's thicker material, you really need to dunk it in water to get it to cool quickly on the inside. If you don't do that, intermetallic phases will form, and that will lower its corrosion resistance. So it is very tricky to do it. People do it, but it requires a lot of skill. What is the importance of ferrite number in welds? What is the recommended acceptance criteria during what kind of applications? Should a ferrite number test be a mandatory check? Okay, so the ferrite number, which is different than the ferrite percent, they're close to one another when you're talking about low numbers, very different when you get to the high ferrite numbers. So, I believe 100% ferrite is actually a ferrite number of 140. So it somehow you have to make sure you know whether you're talking about a ferrite number or a percent ferrite. But as I mentioned, there are you want some ferrite. You would like to have some ferrite in forming in the weld metal as it solidifies, so that you can avoid a lot of issues related to hot cracking. The problem comes when when ferrite actually has a bad influence, and there are a very few corrosion environments where ferrite numbers less than, let's say a ferrite number of 12 or less, or percent of 10 or less, is a problem. Very few, but once you get over that number, there are more applications. And should it be a mandatory check? Well, if it's important, it should be. And generally, you should try to avoid high ferrite welding electrodes that end up with more than 10% ferrite. Even if they do weld nicely, generally more nicely than the lower ferrite ones, you should avoid them. But it should really only be a mandatory check when it is actually significant, and hopefully the engineering company that writes the spec will know when it is significant. So ferrite number on weld properties. Well, the ferrite doesn't really change the strength level a lot. It does make it a little bit stronger to have a little bit of ferrite there, but it's relatively marginal effect there. Even 100% austenitic weld with zero ferrite will generally be stronger than the minimum required for the base metal. So the properties are where you have to be careful, where it's detrimental, which again is certain corrosion environments and also at high temperature applications. Sometimes we are facing issues of fissure-like indications in liquid penetrant examinations in the junction area where Canal 600 weld overlay and stainless steel meets. What could be the reason and how to prevent them? Yeah. When we get into these areas where you have mixed metallurgy, Zinc 600 overlay, so there are parts of that are diluted with the underlay material, which, if I understand correctly, here is 347. Although usually you do 600 on carbon steel, but it's not quite sure. The nickel chrome iron 3 electrode should be a proper one. If it were me facing this, I would actually do a metallurgical examination to determine exactly where the fissures or cracks are. Sometimes you can see things in LPT that are not serious, and other times they go deeper and are serious. So you'd like to see exactly what is happening there. But nothing comes. My first opinion for that particular question is I don't see anything wrong with what you're doing, but you need to do a metallographic examination to actually see what is actually happening, where the cracks are starting there. It may be a contamination issue. The nickel alloys are very sensitive to contamination, but you really have to look for that. Okay, there's another one related to tube sheet joints on a 600 weld overlay. And again, because on an overlay, you have dilution of the base metal, so it depends on whether it's one layer of overlay, 2 layers of overlay, 3 layers of overlay on it to actually know what actually you have on the surface there. And so really we need more information there. And please contact us through the tech service line there and with the details. What about welding 317L? Well, 317L is really a 316L with 1% higher molybdenum content. Also has 1% higher nickel content to keep the welds austenitic like the 316L. 1% higher chromium content for that matter too. It's pretty standard. If you weld 316L in general, you can do it with the same parameters as on the 317L. It is a forgiving alloy. It's used a lot in pulp and paper in Canada, alloy, and people you generally have no problem welding it. What is the effect of nitrogen in stainless steel? Well, nitrogen is an austenitizer. It makes you can divide all the elements into either ones that want to promote the formation of austenite and ones that promote the formation of ferrite in a weld. So nitrogen promotes the austenite phase. In typical, let's say 304L or 316L, the nitrogen content in the base material might be somewhere around 04, 05, 06%. So you have nitrogen there, even if it is not reported on the mill cert, that just naturally happens. It does add strength to the stainless steel. It's one of the reasons why the dual grade 316L is the standard material. They tend to have a slightly higher nitrogen content because the nitrogen makes sure that the alloy is as strong as the minimum requirement for the 316 material while having a low carbon content. There are some nitrogen alloys like 316LN, which have even slightly higher nitrogen content, 0.12 or 0.14%, and they do make it stronger. What else can I say about nitrogen? It does add to the corrosion resistance in terms of pitting resistance. And many of you who have been involved with the corrosion side of things know the pitting resistance equivalent number. There's a strong factor for nitrogen in there. So there's a lot of basically good things that are there. You have a limit to the amount of nitrogen that can be added. If you add too much, you can get nitrides, which are very detrimental. But most alloys will have a relatively low nitrogen content. Does welding of 310 casting require a certain amount of preheat? No. You generally don't want to preheat anything that is fully austenitic, and the 310 castings are fully austenitic. They show linear indications on the weld. So you really want to buy a 310 casting that, first of all, has that is very clean, and I'll think of especially of the sulfur content, also phosphorus if possible, low levels of impurities, because in a fully austenitic alloy, those impurities especially lead to hot cracking. The show linear indications on the weld. I'm not sure if those are longitudinal or transverse. Generally, where you get hot cracking, they're transverse to the weld. Generally, you want to weld them as cool as possible, low interpass temperature also. And a lot of people, when they're trying to do a weld repair, especially of a 310 casting, they want to pour a lot of metal in there, and that's bad. You got to take your time. Small weld passes, very little weaving at all. Just it'll take time, but in the end, you'll get a better quality casting out of it.
Gary, I think there are quite a number of questions, which I think you may take one or two more, and we will be sending you all these.
Yeah.
Maybe.
Okay.
Yeah.
Okay. I'll look forward to that. I'll do a couple more here. Oh yeah. Okay. And actually the next one actually relates to why is 304L welded with a filler metal that is not 304L, it's 308L. So it's got a different number on it, and it's almost like the exception to it. And yeah, it is strange. But 308L has an adjusted composition that is just a little bit higher alloyed than 304L, and they wanted it to be just slightly more corrosion resistant than 304L. So now in practice, the range overlaps, so that doesn't guarantee it actually, but yeah, it is unusual. You don't find 304L filler metal called 304L. It's called 308L, and that's actually in the old American Iron and Steel Institute grades. There is one called 308L, and I understand they were even making wrought products in that grade at one point. Not since I've been around, and I've been around for 50 years, but back maybe in the 30s or 40s, 1930s, 1940s, they did that. And finally, why 316 material after welding area generate ferrite content before welding magnet not attached, but after welding magnet attached, heat affected zone, and welding areas. Well, the ferrite is magnetic, so you know that the magnet will be attracted to the weld. It may on 316L it should not be attracted in the heat affected zone. Now maybe in a casting, well, obviously in a casting it would, because there's material in the heat in the base metal that is there, and but if there's none in the base metal, no magnetic attraction there should not be in the heat affected zone either. So that because the heating up of the base material in the heat affected zone will not cause ferrite to form, although there might be some right at the fusion line. I guess it is possible. So and maybe just quickly, the last one, I'm seeking your expertise regarding a customer recommended using 308L electrodes for root welding and 304 without purging gas. However, during practical welding, we encountered numerous defects at the root. Well, when you say 308L electrodes, I presume you're talking about a bare wire there, and not a stick electrode, because with stick electrodes, you don't normally do a purge of the root. There were some papers that I've read that talk about trying to do that without purging gas. And you do get, well, we call it sugaring, but a rough surface appearance if you don't have purged gas. There are some fluxes you can put on. We're not a big fan of them, but and it really depends on the application. If 304 has good corrosion resistance, and maybe you do not need the maximum there, but we would really recommend either using purging gas for gas tungsten arc welding, or some sort of backing material, or you can do gas metal arc welding. That tends to not have as much problem with sugaring on there. But yeah, in general, you need to do something on the root side. So, okay, so I will leave it at that.
Yeah, thanks, Gary, so much. Because I know it's such a vast subject. It's very difficult to cover in an hour. Yeah. So what we will do is we will send you all these questions. There are quite a number of interesting questions being asked by the participants. Yeah. So we will send it to you over mail, and whenever you get time, you can reply, and then we will pass it back to them.
Yes, I will do that.
Yeah. So on behalf of the Indian Institute of Welding Mumbai branch, we would like to thank you and the Nickel Institute for this wonderful session. And we really now look forward to the next one by Dr. Graham. So we take a break. Thank you so much. Yeah.
Okay.
Thank you for having us. Looking forward to next time.
Yes,
Yeah.
perfect.
Thanks, Jack.
Gary, have a good day.
Thank you, sir.
To everybody, have a wonderful weekend.
Thank you so much.
Sir. Thank you, sir.
Bye.
Bye-bye.
Bye.